Okay, we can go ahead and get started, please. Today, we're going to continue our discussion of hypothesis testing. If you recall, in the DMAIC process, for an analyze, we start typically with some type of qualitative analysis. And from that, we identify some hypotheses. For example, we think there are differences by shift or by region or some machine setting. And we want to decide if or not we have significant differences. And in this case, let's say we want to talk about the situation where we have one y, typically continuous, and one x. X could be different regions, it could be different machine settings, but this time we're going to have two or more levels or groups. For example, we might want to compare region A versus B versus C. Typically, we're doing ANOVA when our X is a categorical. It doesn't have to be that way, but typically when we have a certain number of groups. And usually the number of groups is not like 100 groups. Usually we might have 10 or fewer groups, maybe up to 15 or 20, but usually not too many groups. And we want to have a way to analyze that. We're going to use analysis of variance. By the way, does analysis of variance test the variances? Anyone remember this from class? Analysis of variance is a test of means. We're going to convert mean differences into a variance term, but we're going to use this to test for different mean differences. We'll also talk about the case of how do we do tests for differences in group variances. And then finally, we'll talk about power and sample size planning. Very important, we'll do power and sample size planning for the ANOVA situation, but any type of hypothesis test, t-test, f-test, two-proportion test would be treated quite similarly in our approach, and we should be able to do it for any test. We'll just kind of cover the case of ANOVA as an example. All right, let's do an example how we might apply this. We had a former project that was looking at average fees, and this was related to loans going to 5 different lending institutions. In this case, we have people who are trying to get loans approved, and they're trying to get different fees, and we want to look at differences from 5 different companies or lenders. And we start out with the null, which is we get the same average fees from all lenders. And then there is what we want to test for. This is what we're going to test. We want to know if at least one of these is different from another. Oftentimes we do this to identify, for example, if we have several groups. Sometimes we want to figure out who is Bob and who is Wow. Who is Bob, by the way? Bob is who? Not your friend, best of best, right? And Wow would be worst of worst. So a lot of times when we have several groups, we're trying to figure out, okay, which among these is the benchmark, the better one or two, which one of these is underperforming. Both of these can be quite useful to know. All right, in this case, we're going to have a Y output, fees, which is going to be continuous, and we're going to use ANOVA. By the way, you might say, why can't I just do t-test? Well, if you've got lots of groups and you want to compare A to B, A to C, A to D, A to E, B to C, B to D, B to E, that's very inefficient, right? And it also leads to potentially false alarms. We want to actually just look at them as a collection first, and then we'll do a follow-up if we have significance. All right, that gets us to our topics. We'll go through the case of a single factor ANOVA. Some of you may have learned this where it's called one-way ANOVA. It's called one-way ANOVA because 1x. If you have 2x's, what would you call it? Two-way ANOVA, all right, etc. But we'll do the start with the case of one-way ANOVA. Later in the class, we will do two-way ANOVA and above. Two-way ANOVA and above typically is done using general linear model, if you've ever been exposed to that tool, something we'll cover later in the class. All right, once we have our test, then we're going to test for the mean differences. I want to talk about this idea of using ANOVA to identify what's called a robust operating window. That's a window for X in which Y is insensitive. We'll discuss that. And then we will discuss power and sample size planning for ANOVA, but the same approach would work for other hypothesis tests. Questions so far? Ready to go? All right. If you want to compare two or more means, we're going to use one-way or single-factor ANOVA. A couple things about terminology. In ANOVA or in experimentation, so whenever we talk about experiments and analysis, we use the term factor to represent the X variable of interest, and then we use the word factor level, the value of X. Factor levels are also called treatments. ANOVA in DOE comes from Sir Ronald Fisher, who was studying agriculture, and he was trying to figure out how to optimize the yield of crops. His goal was to feed the world. Pretty noble goal. But anyways, Fisher of the F-test, he is using this for agriculture. So some of the terms like treatments, they come from that. And so we'll continue to use that general terminology. All right, the idea here is we want to test multiple groups. We're going to make some key assumptions. First of all, that we take data randomly selected from independent groups. If you remember with the paired t-test, we had dependent data. In this case, we're going to do this with independent groups. We're also going to assume that the population groups are normal with an equal variance. In other words, your overall distribution could look like this. But if that is A, B, and C, each of these are normal, and they all have a similar within group variance. I might have drew that B a little bit better, but hopefully you get the point of this, right? The overall distribution could be multimodal, but the assumption is that each of the groups has a normally distributed with a similar variance. If you slightly violate this assumption, most people move on. If you are very concerned with your results and you notice that you're violating these assumptions, then we do what's called non-parametric testing. We'll discuss that in our next lecture. So the case with the groups are not normal, and usually we do that when we're really, like, the results make no sense to us. Then we may want to go back and evaluate our assumptions. But most of these tools are what statisticians would say fairly robust to the normality assumption. When we test, we're going to test if they're all equal versus at least one is different from another. We are not going to say that they're all different from each other, right? We're just going to look to see if one among the group is evidence to say they are different from another. If you fail to reject the HO, then you would imply that the mean or the overall mean is not affected by the different levels. We okay so far? All right. If we come back to our commission fee example, I have 5 lenders. These all represent my groups. Lender code is the factor at 5 levels. For each of these, I can compute the mean, the standard deviation, and the variance. Now, when I do this, I may have to define some type of scope to make sure that I'm comparing with similar variance levels. Remember our assumption of we want to have similar variance. By the way, you'll notice in this example that not all the groups have the same sample size. Is that okay for ANOVA? Yes, we don't have to have the same sample size. We might be concerned if we had like 5, 5, and 1,000. That may not be representative or fair, but we don't have to have identical sample sizes. Now, to understand what ANOVA is doing, we're going to make an F-test. And the F-test is going to compare between group versus within group. And the between group variance you can be thought of as this. If I have 5 lenders, each of those lenders has an average. And each of those averages can be compared to the overall average. If this was my 5 averages, so we'll do y bar 1, 2, 3, 4, and 5. And I could draw a straight line basically through all 5 of those averages. I'm going to get a p-value close to what number? If all the means are identical, that means there's no variability. It's going to be a p-value close to 1, right? As the means start to deviate from the overall mean, then I'll start to generate a lower p-value. And this is going to be based, though, on how much variability within a group as a ratio. So again, we're going to figure out the variability within a group. Because we assume that they're all equal, as an assumption, we're going to pool the variances, and we're going to make a ratio. But we're going to see significance when the means deviate from the overall by a larger amount. And we'll use p-values to define how large. How are we doing with that? Make sense? We're looking at the group means, all right? These would all be y bar 1, y bar 2, through y bar 5. And this would be the overall y bar bar would be that line. In this simple example, which means are deviating the most from the overall mean? Which groups? 1 and 4. Very good. So groups 1 and 4 are deviating the most. Now, is it a statistically significant difference? This is what we will test for. We doing okay? Alternatively, you can use the multiple box plot. When you do that with ANOVA, I typically would encourage you to go and add the label for the means, which is a little circle with a plus in it, on the graph. Give you a sense of that. Alternatively, I like interval plots as well. You can make an interval plot to compare them. We'll use both of these tools, or individual values plots also can work. As you look through 1 through 5, there is this question about constant variance. Just looking at that graph, there appear to be any potential constant variance concerns. Yes? So group 4 data seems to have a lot more variability than the others. We want to test for that, which we will. All right, to do an ANOVA analysis, we're going to test our assumptions, of which there are 2 main assumptions. And then we're going to look for a mean difference. And if a mean difference exists, then we'll follow up. We'll either do pairwise comparisons or some visual analysis, or in some cases we may rerun our ANOVA testing for differences. Show all that coming up. All right, 2 key assumptions. The first one is the HOV assumption, homogeneity of variance. We're going to assume that if we have groups A, B, and C, that the variances of the groups are equal. If you want to test for equal variances, if you assume normality, if you assume the data are normal or the groups are normal, then we use what's called a Bartlett test. If it's non-normal, we can use a Levine test. Or Levine can be used for either of them. This idea of testing for variances before we test for means is not new to us. When we do an X bar chart, what do we look at first? Do an X bar chart, what do we look at first? They come in pairs. Which one do we do first? Range. Thank you for playing. All right, we do a range chart. All right, if you step back and think about that, range chart is a test of homogeneity of variance. You want to have the within group variability as assessed using a range chart in control before we start to evaluate the X bar chart. We mentioned before, if the range chart's out of control, then what happens to the control limits on an X bar chart? They get arguably artificially wider. Therefore, you might miss things. Same thing can happen here, right? If you have differences in the variance, this could affect things. Now again, most of the time it never comes into play, but if your results don't make sense, this is one of those things that you may want to look closer at. All right, the second big assumption is that the residuals are normal and independently distributed. Now, you may think about graphs A, B, and C that I drew up there. Once I account for the differences in the means, the residual is what's left over in the fitted value. Therefore, when the residual is basically the overlay of those three graphs, once I adjust for their mean differences. Therefore, we can look for normality by looking at a residual distribution. So we look for our residuals to be normally distributed. We'll also assume that our data is independent, meaning we don't have any trends over time in that. I do want to point out that if you are concerned about your assumptions, you can use a non-parametric. We will cover that later. Although if you read enough statistical books, most statisticians will tell you that these tests are fairly robust. So even if you violate an assumption, probably your results are probably still going to be valid. But again, you can double check that with a non-parametric. All right, let's go ahead and do that. To test for equal variances. The null hypothesis, right, is the variances are going to be equal. The alternative is going to be at least one differs from another. And we can do that in Minitab, Stat, ANOVA, test for equal variances. We put in our Y and we put in our X. Under the options command, I'm going to ask you to check on the box that says use test based on a normal. This is going to give you a Bartlett. If you run this test and you do not check the normal, Minitab is going to return the Levine for you. Rarely will they give you a different conclusion, but they'll certainly give you a different p-value. Are we okay? Normal will pick the Bartlett test. And we do that, and Bartlett comes back and gives us a p-value of 0.215. And from that, we could say that there is no difference. Even though group 4 looked like maybe there might be an issue, we don't have any evidence to suggest that. By the way, what else can I look at from this graph to make the assessment of no difference? We can do what? If we can draw a straight line through all of those confidence intervals, this would also suggest no difference. If we do have a difference, we could ignore, because most people will never realize it anyways. We could run a non-parametric. Or we sometimes just need to collect more data. Maybe we don't have enough data and we have an outlier point or something like that. Could be going on. Especially given this graph right here, you'll notice that you have a kind of a wider confidence interval as well. All right, how are we doing? We okay? Some of you don't like these kind of comments, but this is what happens sometimes, right? We have a slight departure, but we decide to move on and use the ANOVA test anyways. If our results are logical, we may be okay. If we're concerned with our results, then maybe want to rethink this. Kind of a practical answer to this question. Moving on, test for variances. Then we have our residual test. Under the graphs for one-way ANOVA, Minitab has this tool called a 4-in-1 plot. It's a classic way to look at residuals. If we do that, we get the following 4 graphs. By the way, to refresh your memory on what a residual is, you run data, you fit a model. From that model, if you tell me X, I'll predict Y. But if I know what the X actual was, I can compare X actual or Y actual to Y of the fitted model. The difference between that is called the residual. If the model fits the data perfectly, the residual equals 0. You will get residuals that go above and below 0. This is by definition. It's like best fit line through data, some above, some below that best fit line. We want these residuals to have certain properties. To test for normality assumption, same thing if you took a regression class. You would look at these 2 graphs over here, and a couple things you would notice. If you make a normal probability plot of the residuals, you'd expect the residuals to do what if they're normal? Fall along the line, right? You make a normal probability assumption, they would fall along the line. Or if you made a histogram, they should look like what shape? Like a bell. All right. Everybody clear on that? You might say, what might be a case when it doesn't look this way? It's possible sometimes that your residual plot might have a little horseshoe kind of look to them. This is the one, if it's really bad of a horseshoe, you might be a little bit more concerned. We'll talk about that later in general linear model. We'll fit more sophisticated or complex models. By the way, if you look at this graph over here, this is a graph of the fitted value versus the residual. If you look at that, how many columns of data do we have? How many fitted values do we have?
5.
5. Why do we have 5 fitted values?
5 factors.
We have 5 groups, right? When you have 5 levels or 5 unique groups or 5 unique X values, you'll get 5 different columns. What we'd like to look there is we get a similar range at each level. We want a similar range at each level. Sometimes it looks like a funnel where we have a lot of variability at certain levels and very little variation at other levels. This would be a concern. When we put the data in order, we're looking for any time trends. If we don't have our data in order, we should ignore that graph, only if we know the order in which we collected it. How are we doing? Are we okay? All right. Official 7-second pause. Catch up with me. All right. We've validated our assumptions. Homogeneity of variance with the Bartlett test. None of the residual issues look to be of a concern. We are now ready to analyze our results. Minitab will give us a one-way ANOVA table. This table has an F statistic. This F statistic is going to be a comparison of between group variance and within group variance. When this number gets further and further away from 1, then we'll get lower p-values. In this case, we get a p-value of 0.003. This is clearly significant. So we have a significant difference. We're going to reject the HO. By the way, this error term, there's a value here. It's called the mean squared error. Mean squared error is like what's left over after you fit the experiment. If you take the square root of the mean squared error, you will get what's known as S pooled. You take the square root of the mean squared error, that's like what's left over after fit. That's when you get the standard deviation pooled. This is also known as the standard deviation within group. I wrote in the board up there, standard deviation within group or standard deviation pooled. It's what's left over after fitting. Doing okay? This number right here is just, the square root of the mean squared error. Call it the pooled standard deviation. This pooled standard deviation is what's used to help us generate these intervals. The other thing that affects the interval plots is the sample size or subgroup size. The intervals are going to not all be the same if the subgroup sizes for each group are different. And when I look at these, if I do that, what can I observe? First of all, it looks like 2, 3, and 5 are what? Pretty similar. What do we observe? Which ones are different from which others? Or different from? Certainly 1. And 2. Some differ from some others. Some are similar. Kind of depends on which way you draw your straight line. But what we learn here is we have at least one differs from another, is what we say. We don't say that they're all different from each other. That's important to me that you understand that. We doing okay? All right, I will certainly ask you questions on homework, then again on tests, final exams, every chance I get. Some of you will pay attention now and you'll remember this. Others of you will get these wrong on tests, but I gave you fair warning. I don't know what else I can do. When I tell you a p-value for something, let's talk about what it is and what it is not, right? A low p-value from an ANOVA test does not tell you that all means are different from all others. This is not true. It does not suggest either that the within group variances are different. People hear the word ANOVA and they think that the result tells them that the variances are different. A Bartlett or Levine test is used to test for different variances. We convert means into a between group variance term to apply ANOVA. But the variances of the groups are not analyzed with ANOVA. That's with the Bartlett. And then finally, just because we have a statistically significant mean difference does not necessarily mean that it's useful to know or useful practically. Sometimes we have mean differences between things, but they're relatively small effects, and they're just kind of noise. I could have two different machines which are statistically different, but maybe they're both producing everything in specification. Therefore, it may not be worth it for me to figure out why they're different. Other times, one machine is out of specification, the other one is in. Now it's up to me to figure out why. The idea of practical significance. Are we okay? Are we going to get this right in the test? Confidence? All right, we'll see. Now, if a statistically significant difference does exist, now we need to determine which group is different. Now here there are like quick ways and more fancy ways. Most of the time the quick way works. If I'm a little bit concerned, there are some more advanced ways. The quick way is as follows. You look at visually box plots and confidence intervals, and then you refit. If you were to look at the following graph, which one might you pull out? I might pull out group which one? 4. The other ones appear to be the same. Just visually, I might do that. If I wanted a more rigorous approach, I could use what's called analysis of means, or I could do what's called post hoc mean tests, mean difference tests. I'm going to put these outside of scope. But if you ever had a class with a Tukey test or a Fisher test, these are all perfectly legitimate. Turns out that most of the time visual method works, but once in a while you get more complicated ones. If you use the Minitab Assistant, it will automatically do these tests for you as part of the analysis. All right, how would I do that? This is a good time to remind us about some of the nice features in Minitab. For example, the subset. If you wanted to, you could simply take out group 4 and then rerun the analysis. So I've created a Minitab subset command, and I said don't pick group 4. I rerun the analysis. I get p greater than alpha. I can also draw a line through there, and I would conclude that there is no difference or no significant difference. Would be another way to say that it looks like 1, 2, 3, and 4 are similar. I'm sorry, 1, 2, 3, and 5 are similar. 4 appears to be different. Are we okay? A classic question could be, okay, well, if 4 is different, how do I figure out how much different? Right? We often use statistics to say whether or not things are different or not. Then people want us to quantify that. How do you think I could quantify how much different? I'm going to do a mean difference between 1, 2, 3, and 5, and 4. All right, as an aside, a more formal test would have been to do an analysis of means. You will see this shown here, and this one is showing up as different. Now, by the way, when I do this test, you'll notice that the green line is the overall mean, and then the red line become these intervals, confidence intervals. The confidence intervals are changing because the subgroup size is changing. Same thing we had before with our SBC. When subgroup size varies, the limits change. Limits get tighter when the subgroup size goes up. They get wider when the subgroup size is relatively less than the others. All right. A lot of times people say, okay, well, you've told me they're significantly different, but is it practically significant? That gets to the question of how much the mean differs. One way to do that is to recode your data into lender 4 versus not lender 4. Come up with a way to 0 and 1 or some type of binary indicator. And when we do this, we would find that group 4 has a mean difference of 1,050. That would be the difference versus the other groups. Now you got to follow the logic a little bit. If you tell me that groups 1, 2, 3, and 5 are all the same, I'm just going to group them all together. Right? That's just more samples to get a better estimate of the average. Let me compare that to the lender 4 to do that. By the way, in this case, we have a p-value of 0.001, which is what we'd expect. And what about the 95% confidence interval of difference is interesting. You see where it says 95% confidence interval of difference is 466 to 1635. What is interesting about that? It does not include what value? Not the group 4 mean. The difference does not include a 0, right? When it doesn't include 0, that means that the distribution is shifted. We're not surprised by this result, right? Because of what we've already done. Questions? Yes?
You say it doesn't include 0. I guess, could you explain a little more?
The question is, what does that really mean? So if I look at the mean difference, the null hypothesis would be that the difference equals 0, meaning that the mean of 4 is equal to the mean of 1, 2, 3, and 5. If this was the null hypothesis, this is the same as saying that the difference equals 0. Mu1 minus mu2. And my null hypothesis is the difference equals 0. And then when the confidence interval does not include 0, that means I have a significant mean difference. And that significant mean difference as a value would be 1,050. We okay? All right. There are different applications of ANOVA. Sometimes we do ANOVA because we have different groups and we want to try to understand who's doing better or who's doing worse. Certainly is reasonable. Other times we want to use ANOVA to basically show that our process is robust to a variable. As an example, you could have a process where you have 5 different operators. If you wrote really good standardized work, you would expect all 5 of the operators to have the same average process time. If you wanted to test for that, you could do an ANOVA test to see if there was any differences. And look at them across all 5 and see if anyone is doing anything different, either better or worse. This is a robustness study. You're trying to figure out if your process is robust to some variables. That would be a categorical. Other times people do robustness as a test of some continuous x. For example, you might have a machine, and the machine could have different speeds. And people may want to know, if I increase the speed, do I change the performance? Or I could have different temperature settings. And I may want to be able to say, you know what? If my temperature is between 100 and 150, I should not have any mean differences. I'm trying to figure out if there is some relationship. And in other words, I'm doing the test to basically show that there is no difference in the means. ANOVA is a classic way to do this. Again, we're going to assign a factor as our treatment to see how robust we are to that. All right, this is a former student project. This was looking at the distance of the nodes for like wireless communication. So we have a wireless service in an office building, and they have some nodes are closer than other nodes to each other. And they're trying to understand how close do these have to be in order to get the highest reliability in terms of information going back and forth. In this case, they have a metric, which they use the PRR, and basically what they do is they send 2,000 pieces of information through their network, and they configure it different ways, and they see what it comes back to as a score. Should be as close to 1 as possible. And then they want to evaluate how robust X is in terms of distance versus the PRR. Now, you might be thinking this could be a nice regression problem. And it could be. But maybe you have complications. You don't have as many of all kinds of different numbers. You want to kind of put them into 3 groups. Less than 5, 5 to 10, and greater than 10. I'm going to put them into 3 ordinal groups. By the way, this becomes an ordinal variable. All right? They run the test, and they get as following. They get a p-value of 0, which is not ideal in this case because they did not have robustness to any size, but they learned something rather interesting here. What did they learn? If they set them too far apart, what happens to the PRR? Becomes too low. That's one conclusion. But a equally useful conclusion is that as long as they set the nodes less than or equal to what number? Less than or equal to 10, they should be okay. It's a rather simple example, and it was a clear result. There wasn't really much mystery behind it. But it's a good example to help us see that when you have many levels of things, sometimes we're trying to figure out how robust we are to different settings of X, and this is often a good thing. If you are in the world of design, right, you want to design things to be robust to noise variables, and we can use ANOVA to validate our robustness. Questions? All right, last topic of the day. I'm going to talk about sample size planning. We're going to do this for the example of ANOVA, where we're trying to figure out or detect a mean difference. But if you're inside of Minitab, you will notice that there is sample size planning for t-tests and two-proportion tests. All kinds of hypothesis tests have them. And Minitab is actually a little bit limited. You could go online and find software that has more power and sample size for even more statistical tests out there. It's really quite a common thing for people to want to do. All right, the idea of power and sample size planning is to understand your sample size and the condition of your experiment. What can you detect? What's a reasonable value you can detect? Or how many samples do I need? Now, I will say this. I've done this many times for people that say, hey, can you tell me how many samples I need? And I do a thorough power and sample size analysis. And I tell them you need like 100 samples. And they come back and tell me, oh, that's way too many. We can't do that many. We can only do 30. I say, okay, then do 30. But I will do what you asked me to do. But a lot of times we do power and sample size planning. And the reality is it requires us to have larger samples than a lot of people are willing to pay for. And then we ended up kind of backing down from them. That's okay, as long as we understand what the limitations are when we do that. It's a really useful tool to understand what we can gather from our experiment. All right, the idea of power. Power is 1 minus the beta error. Beta error is the type 2 error. And it's also known as the fail to detect a difference error. So fail to detect a significant difference. In other words, you fail to reject the HO when you should have rejected it. All right, when you do power, you have to assume some amount that you're trying to detect. People say, what's the power of the experiment? You'd say, well, you got to tell me what it is that you're trying to detect, because power of an experiment is going to change based on the amount of difference you're trying to detect. Are you trying to detect a change of 5%, a change of 50%? Depending on the answer to that question, your power is going to change. All right, let's go ahead and think about this. This mean difference effect, this is the amount. This is the amount you're trying to detect for to conclude a shift. This amount should represent a practical significance. You say, you know what? If the process shifts by 0.5 millimeter, I want to know that. Or if the amount of fees is more than by $500, I want to know that. You have to tell me what, or tell what you think is useful information. All right, to illustrate an example, let's say you had the case where you have an average process time is 4 minutes, and you have a standard deviation of 1. And there's this question about, would you want to detect a shift of 1, or you maybe want to detect a shift of 0.5? Are you with me? If you want to detect a shift of 0.5, that's a smaller shift. Are you going to need more or less samples than if you're trying to detect a shift of 1? More or less samples? Probably going to need more samples. Right? And the question is, how many more? This is why we do power and sample size planning. We identify an amount of a shift, and then we say, well, if I wanted to be even more or even less, or what am I trying to get to, all of this stuff is based on power and sample size planning. To do power and sample size planning, we begin with some assumptions. We're going to make an assumption about our type 1. When in doubt, we set it equal to 0.05. If you want to change that to 0.1 or 0.1, that's fine, but that's usually our baseline. If you're going to do this with ANOVA, you got to figure out how many groups are of interest. Differences between 2 groups, 3 groups, 4 groups. If you're doing a t-test, obviously just have 2 groups. You also need an estimate of the inherent standard deviation. This could be sigma inherent, sigma within, sigma pooled. These all mean the same thing. Now, if you remember our assumption of ANOVA, one of our 2 assumptions was homogeneity of variance, which means all the variances are equal. All the within group variances are equal. If they're all equal, we've got to give an assumption of what that number is. We've got to know what that within group variance number is as an estimate. These are our assumptions. Then there's 3 levers we can pull. We can tell me the amount of difference in sample size, I'll compute the power. Or tell me the power in the sample size, I'll tell you what difference you can pick. In other words, you give me 2 of those 3, leave the third one blank, and then let the software answer that question. The idea of power and sample size planning is you have these 3 variables of interest. Tell me 2, let the software get the third one for you as an estimate. Make sense for you? You need, identify, or assume 2 of the following 3. Again, we can do this for means, for variances, for proportions, etc. Let's say we come back to our lender example. We've got 5 groups. Let's say we start out with this idea of, let's assume that we're going to go out and we're going to get a sample of 10 from each. Kind of ignore the actual experiment we already ran, but we're going to go out and say, you know what? I think I can get 10 for each group. Then someone has to say, what is your alpha? That's your 0.05. Someone has to say, what is your assumed standard deviation? This is your sigma within. Let's say based on historical data, if I gave, say, the similar loans to the same person, I have a standard deviation of 500. By the way, do you think we always know this number? This can be a hard number to estimate, right? This is where it helps to have like control charts. If you have control charts, you have an in-control process, it gives you a better feeling that you have a good estimate of sigma within. Or you could do historical ANOVA test and get a sigma pooled and use that historical number as your answer. A lot of times it's based on historical data that you would gather. All right, the next big thing is you have to tell what you call a practical significance. Let's say you want to be able to detect $600. Sometimes people say to you, I want to be able to detect a 10% change. You'd have to convert that to a number. So if the mean was 500 and you want to detect a 10% change, you have to convert that to an actual number. But this is what we're looking for. If you read literature on this, though, sometimes expressed as an amount, sometimes expressed as a percentage. We'll convert it back to an amount. What we're doing here is we're leaving the power blank. Remember, we had to pick 2 of 3. We're going to leave the power field blank. Are we okay? If we go ahead and do this, my power to detect the mean difference is calculated for me. Minitab came back, tells me alpha, my assumed standard deviation, my number of levels, and it comes back and says my mean difference has, with the groups of 10, only has a power of 0.5. You would have a 95% confidence level, that's the false alarm, but if the mean shifted 600, you would only catch that 50% of the time. By the way, if I look at the maximum difference to the standard deviation, what's roughly the relationship between them? Pretty close to a 1 sigma shift. 600 is pretty close to a 1 sigma shift in this example, right? The mean difference amount is pretty close to standard deviation. See what I'm doing there? The mean difference you're trying to detect is 600. Standard deviation is 500. That's pretty close to like trying to catch a 1 sigma shift. If you can visualize a 1 sigma shift, pretty good chance that you're going to miss that. If the mean difference effect was, say, 2,000, the power here would be high or low? Really high. I'm going to be able to detect a 4 sigma shift. Right? If the mean shifts 4 sigma, I should be able to detect that. But as the mean difference gets closer and closer to the standard deviation, then the power, I'm going to need more samples probably. All right, so in this case, we start out with a baseline power of 0.5. And your person you're running the experiment says to you, 0.5, I want to have a higher power. A good rule of thumb for power is, say, 0.9. If power is 0.9, beta equals what? 0.1, or there's a 10% chance to fail to detect the difference. All right, what things can I do to increase the power? How could I increase the power in this experiment? What would be the easiest way? Good. That's just kind of our own logic. Increasing the sample size would be a good example, right? So if I have more data. Anything else? Pardon? I could change the alpha value. What else? I could put the power in there, but I could, if I put the power in at 0.9, I could let it solve for sample size, or I could let it solve for what else? I could set the power of 0.9. I could then solve for sample size, or I can solve for
Value's maximum difference between.
maximum difference amount. Right? If I had a maximum difference amount was higher, what would happen to the power? I'd be able to detect. I'd have more power if I'm trying to detect a larger difference. The other one, which is a little tricky to understand sometimes, is that if you have a more controlled experiment and you can take the sigma within and drive it down, then you can also get more power. If you take a more controlled experiment, fix more variables, lower your sigma within, you should also be able to do that. But let's explore this. Let's say you decide to put the power in and solve for n. I should be careful there. I'm going to solve for little n because it's going to be per group. And when I do that, Minitab comes back. Here's the max difference. Here's the target power. The actual power will be slightly different because I'm going to work in whole units. Sample size can't be 22.987 because I'm going to work in whole units. And it's going to come back and tell me that I need 23. To increase the power, you'd have to go from 10 to 23. Now, is that 23 total? People forget this all the time. This would be 5 times 23. Is that 115? This is just the per group. All right? Also a classic question. Yes, question for me.
Power like you were before, and you already had your sample sizes, when you input it, if there are unequal sample sizes, would you take the average?
Can you speak a little louder? I can't hear you.
So if you have unequal sample sizes and you're trying to solve for power, do you put the average number of your sample sizes in the box?
Typically we do that as averages. Yeah, there's not a way to, the question is what if we have, we want to do power of our experiment and we've already collected data and we have unequal sample sizes. We'd have to come up with a rough idea, and to do that we would average the n. There's not a way to do it individually, and there probably is with some really advanced software, but I'm not aware of it. But so I would just average the n and get close enough for that. Are we okay? All right. Sometimes what we would do is we actually make what's called a power curve. I could come over here into one-way ANOVA. I could leave the power field blank, and I could have 20, but I could also just do it for a bunch of different sample sizes. And if you do that, you get this famous thing called a power curve. You may have heard this before as an OC, operating characteristic curve. You took a stat class, you may have seen that before. Basically what you have here is you have the maximum difference and the power. And you get this for different lines for different ends. And what you can do is, given some maximum difference, you can see the effect of the sample size. For example, if the maximum difference was 400, if my sample size is only 10, that's a power of 0.2. That's not very good. If I could take that 10 all the way up to 50, now my power gets closer to 0.9. If I wanted to have it really high, I would need 100 of each. But I can do power curves to look as I go up to see what the effect of different sample sizes would be. Or I could go the other direction to see what the effect of different mean difference effects would be. And what hopefully you're seeing there, if you study this a little bit, is that as the mean difference effect gets larger and larger and larger, I need fewer samples to see that. This is actually a rather important finding. If you're studying something and you have method A, B, and C, and you're pretty confident that method C is way, way better than A and B, you really don't need a lot of data to show that. If you have A, B, and C, and you think that C is slightly better than A and B, you probably need more data to show that significant difference. How are we doing? Questions? When you deal with proportions, we can still do power and sample size planning. When we do proportions, we set it up as follows. You would start with a baseline proportion. I would give you a problem, and I would say the baseline P sub 1 is 0.85. And I might say, I want you to detect an increase of 0.1. So a 10% increase. Maybe you're doing yields, and you want to know if I can detect a 10% increase in a yield. I would make my comparison. I have to convert that to the same units. So if it's 0.85, 10% increase would be 0.95. By the way, it actually matters which one you put where, right? Because proportions are not symmetric. If you look at a proportion curve, therefore it depends on which is baseline, what's your comparison. We try to get those correct if we're going up or down from a baseline. In this case, let's say we start with power, and we want to solve for n. If we do that, the software would come back, and it would tell us we need 153 per group. Question for me.
One is 9. So our baseline is 1 or
Oh, the baseline, so I'm sorry. Baseline is P2. I didn't say that right. My bad. I don't really like the P1 and P2 as much as I like the idea of making sure that there's a baseline and what you're comparing. They have it set up as P2 and P1. So I'm sorry, I think I said that wrong. My apologies. But most important is to read the word for baseline and then what you're going to compare it to, and then follow the questions over here. Thank you for that. That just seems wrong to me. Baseline should be 1, and what you compare to be 2, but Minitab is more powerful than I, so I can't stop them from doing that. But that doesn't logically make sense to me personally, so sorry about that. All right, we got a little, getting back. If we run this, we need 153. As kind of makes sense, you need a lot more samples when you start talking about proportions. Let's say you're trying to call a presidential election, and you were somewhere and the percentage was like 50.1 to 49.99 to 50.01. How many samples do you need for that? You need them all. You pretty much need them all, right? When you start looking for very small proportions, right, you need a lot of data. But when you're watching, for example, the election results of a political poll, right, and they start calling the election early, that's because they're doing power and sample size planning, and they're saying the probability of me missing this difference gets really, really low, therefore I'm going to call the election. Now, they'll call the election early when it's like 55 to 45 or 60-40. If you get to the point where it's pretty much 50-50, then they're going to wait to the wee hours of the night because they don't have any confidence in that. They don't have any power to detect such a small difference. In fact, what really gets interesting, if you like election politics, if you get to the certain point of, say, Florida years ago, the difference was so small they could never call it because the error associated with the collection of data was higher than the difference between the two candidates. So when the error gets to be higher than the difference between the two candidates, then you're just basically flipping a coin, and whoever wins it, right? That's the luck of the draw in that world. But that's the statistician's view of things. Probably politicians would think otherwise, but that's really what's happening, right? You have margin of errors that you can't detect because of data collection systems in that period of history. All right, moving on. This gets me to what I would argue as the 4 key lessons of power and sample size planning. I'm going to encourage you to take what I've given you and run through these to see if you can match each of these results. but they should all hold true. If you have a fixed n, meaning you decide this is the subgroup size, as alpha decreases and beta increases, right? So if alpha goes up, beta will go down, power is reduced. Alpha is 0.05, and you decide to make alpha 0.01. Think about this logically. If you make alpha of 0.01, what you're going to do is you're going to now make your confidence intervals wider. And when they become wider, you're more likely to miss the difference. If you have two confidence intervals and they both get wider because they're 99 versus 95, those intervals will be wider and you'll have a little bit more overlap and you're going to miss things. Alpha goes down, you will do that. So if you want power to go up, you take your alpha value and do what? You increase it. Let you play with that a little bit. The only way to simultaneously change alpha and beta errors is more sample size. All right? Because if you have a fixed sample size, they start to trade off. All right, number 2. If you have large mean difference effects, so high magnitude of differences, you need smaller samples. In other words, you want to have more power, look for larger shifts. Someone says, I'm trying to detect a shift of 100. Are you sure? Is 300 okay? Yeah, 300 is fine. You want a larger shift, you'll get more power. As sample size increases, power goes up. And as the standard deviation goes down, power goes up. And the way to remember that one is think about controlled experiments. If you control the experiment and you have less noise, you'll have less sigma within a group, and you'll be able to have better power to detect differences. If you have an uncontrolled experiment, that's going to change. A side note, which has more power to detect the difference? A paired t-test or two independent samples t-test? Which you think to detect smaller differences? Paired t-test? Paired t-test. Paired t-test is going to detect smaller, have the ability to detect smaller difference or be a more powerful test. All right, wrapping up for today. When I tell you to do one-way ANOVA, that's the test for mean differences between two or more groups. If you get a p-value that's significant, you're telling me that you have at least one different from one other. You're not telling me that the means are all different, and you are not telling me the within-group variances are different. And you're not telling me that's actually practically important. If you do have a difference, we can follow that up, either with confidence intervals or analysis of means or other methods. We talked about using one-way ANOVA to identify a robust operating window. And then finally, power and sample size planning. You have sample size, you have the power, and you have the amount you're trying to detect. And you should be able to play with two of any of those three and solve for the third using the assumptions for the other parameters. All right, questions before we wrap up? All right, sounds good.